Hello YouTube. Today we continue our discussion of simple electricity, and our goal today is to demonstrate how to measure current voltage characteristic and explain what it is. So we will use these two objects of our measurements, and this will be a resistor, 1 kilo ohm resistor, which we used in previous discussion when we introduced series and parallel connection of resistors, and blue light emitting diode. So let us first define what is current voltage characteristic, and for that purpose let us draw such a electric circuit. So we have some power supply, DC power supply, then we have a resistor which will be used for measuring current voltage characteristic. Then we will have ammeter, which is connected in series, and so this circuit is closed. Here we will have a voltmeter which is connected in parallel to our resistor. Here we have power supply with certain polarity. We can also change polarity to have symmetric current voltage characteristic and measure it in both directions. So it can be also switched in polarity. So this is simple electrical circuit which allows us to measure current voltage characteristic. So current voltage characteristic is a dependence of voltage, current versus voltage. So depends what kind of device we are measuring, just resistor or some more complicated electronic device as a light emitting diode. We will have different curves which describes this current voltage dependence, and that's our goal for today, to be able to do this measurement and demonstrate how different current voltage characteristics can be for different devices. So let me consider our instruments which we are going to use, and here we have power supply which we will use for providing potential difference and as power, DC power supply in our circuit. So we will need two multimeters which will serve as ampere meter and voltmeter. So this one which is in the right side, this will be our ampere meter, and let me turn it on. Yes, so here we go for milliamperes, and here we go for volts. So now what we need to do, we need to connect ground terminal with negative terminal of our power supply. We connect our resistor, and then it comes to positive terminal of power supply. So that means we have our resistor and ammeter connected in series to our power supply, which is outside the field of view. So let us now run some current. So you see when I change the voltage at power supply, we have some current flowing through the resistor, and it is measured by ammeter. So that's good. Now, in order to get current voltage characteristic, we need to connect also voltmeter in parallel. So we connect in parallel to our resistor voltmeter. And now we look simultaneously on both. So I changed some voltage at power supply. So now we see that we have here around, let me change like quite sensitive. So we have around 2 volts voltage drop over this resistor. And we have about 2 milliamperes flowing through the resistor. So we know that now we have all information to start measuring the current voltage characteristic. So let me come back to 0. So here is our sample. And in order to have some data, let's make a table here. So this is voltage in volts, and here is current in milliamperes. So we can start increasing the voltage at power supply, so and monitor what's happening here. So let's go first to 1 volt. It's around 1 volt, 109, and we have 1.10 milliampere. So let us go higher. So let's say 2 volts. And so it's 2.4, and here is 205. So we have 2 volts and 2 milliamperes. We can go further. Let's go to 3 volts, 3.06, and here is 3.04. 3.06 volts, 3.04 milliamperes. Let us go to 4 volts, 402, and here is 401. And let's do 5 volts. That will be enough for our demonstration at this stage. So it will be 5.05, and here is 5.05. So as you see, there is quite a correlation between voltage and current. We use 1 kilo ohm resistor for this demonstration. You can determine resistance by dividing voltage drop over current following the Ohm's law, and pretty much for all these readings we get 1 kilo ohm, because this is milliampere, so 10 to minus 3 ampere, and here we have volts. So what is interesting to demonstrate here, let's go to 0, and at the power supply. So at the power supply, I will change the polarity. So I will replace positive and negative terminals. So now let us make a line here to separate forward and reverse branches of current voltage characteristic, and we can start applying some voltage. So here we see negative sign and also negative sign on voltage and current. So we are going to the reverse bias. So we change polarity of applied voltage to this resistor, and obviously current direction also changed. So let us go to 1 volt, like minus 1 volt. So here it is, minus 1.5 volt, and what do we have with current? Also minus 105 milliamperes. Let us go further to more negative bias, which is minus 2 volts. Here we have minus 2.1, and here is minus 2.01. So let's go to minus 3. Minus 3.04. Here minus 3.01. Next step is minus 4. Minus 4.05. And here is minus 4.04. And we go further to our last point of measurement, which will be minus 509, and here is minus 509. So let us go to 0, and now we can look at this data which we just measured. So we see that this correlation between current and voltage, applied voltage and current, remains the same at reverse bias as it is for forward bias. So what it means, we have symmetric current voltage characteristic. So you can do it yourself. We will not make like some input of each of these points on current voltage system of coordinates, so you can do it yourself if you're interested. However, based on this data, we can show that for a resistor, current voltage characteristic, so here we have voltage, here is current. So in general, we can use another color for this curve. We will get something like this. We have linear and symmetric current voltage characteristics. So we can connect these points, and that is current voltage characteristic of a resistor, and magnitude of resistor will be defined by this angle alpha. So if we have a smaller resistor, this angle will be larger. If we have a larger resistor, this angle will be smaller. So the key thing here that no matter if we apply positive or negative volts to polarity to our resistor, we will get the same magnitude of current flowing through this resistor. So we have linear and symmetric current voltage characteristic. So let us check another electronic device, which is blue light emitting diode. So we will do pretty much the same. We will first of all, we will put the right polarity at the power supply, and let us connect the resistor. Oh, sorry, that's LED. So what do I do here? Here, and we need to connect also. So this is we have light emitting diode connected in series to ampermeter. So now when we apply some voltage, yeah, we see light emitting diode starts to emit light. So that is forward polarity. We have some current flowing through this light emitting diode, and that converts electric current into photons of blue color. So in this case, I would like to start our experiment from reverse polarity, and then we will go to forward. So now let us connect in parallel voltmeter, because we also need to monitor voltage drop over this LED. So we connected in parallel our voltmeter. Now again, let us do this table. We have voltage in volts and current in milliamperes. So let us apply some negative bias. So you see we have this negative sign. However, what is interesting that, so here we have minus 1 volt. Let me do something close to minus 1 volt. Okay, minus 106, and there is 0.0 milliampere. So we applied reverse bias minus 1 volt, but there is no current flowing through this LED. So now let us go to -2 volts. Need to be careful when we apply reverse bias to LEDs because we can damage it. So now we have -2.05, and surprise, there is again 0 milliampere, no reverse current. Let us try -3 volts and see what will happen. So we apply -3 volts, -3.01, again 0, there is no current. Looks like either something wrong with our electric circuit, or this device, light emitting diode, doesn't allow current to flow at reverse bias. Most likely everything is okay with our electric circuit because we double checked that forward bias and device was working. We could see some blue light and current flowing through it. So let's try -4 volts. Well, nothing changes, -4.04, and we still have 0 current. This current actually probably not equal to 0. Let us try to go to microamperes. Well, yeah, now we see that there is some negative current because we have negative polarity, and very, very small reverse current, which is 0.002 milliamperes. So 1 milliampere, it would be here because now we are in the microampere and the highest sensitivity of this multimeter. So we have 0.002 milliamperes, which is 2, this is equal to 2 microamperes. So this is really, really tiny current flowing through this resistor at quite large reverse bias. I wouldn't go to -5 volts just to be sure that we don't burn the light emitting diode. We still will need it in the future. So now let us go to 0. Put this line here that defines that we stopped measuring in the reverse bias, and now I put polarity of the power supply in right configuration, so we can start measuring now in forward bias. So let us see what happens. We apply 1 volt in forward bias, 1 volt. Okay, so we have now plus 1.02. Again, there is no current. We can actually switch to milliamperes so to be consistent, and here is 0. So again, kind of looks like we have no current at when we apply some forward bias to this device. Let us go to higher forward bias and see what happens. So here will be 2 plus 2 volts, 207, and we still are at 0. Similar behavior as we observed at reverse bias. Okay, let's go to 3 volts. Oh, something is happening. So we see, first of all, we already start to observe light emission from this LED, and simultaneously there is some current measured in the electric circuit at 2.5. Let's try to set it, oh, like 2.4, barely visible. I'm not sure if you can see in this camera, but it's very dim, and no current, but already at just a little bit higher voltage, which is 2.53, we have 0.14 milliampere, and it's already visible blue light emitting from this LED. So let's see what happens further. Let's go to 3 volts. Oh, you see, at 3 volts this LED becomes very bright, and so it's plus 3.08, and we have already 18, actually 19 already, 0.2 milliamperes, and this current is increasing. What's happening now, we run quite large currents through the LED, and we start to warm it up because this current dissipates heat. LED's LED's temperature increases, and it lowers potential barrier for electric current. So potential barrier drops at fixed voltage. We observe some increase in electric current which flows through this LED. So obviously, if we see such thermal effects by increasing current in LED, we don't want to go to much higher forward bias, because then current will be very high and we will just burn the LED. So at this point we can reduce this, eliminate the forward bias, switch it to 0, and let us look here on our data. So we clearly see very asymmetric electrical conductivity of this device, asymmetric current voltage characteristic, polarity dependent. So at reverse bias, starting from small to large reverse bias, pretty much nothing was changing. We had no current flowing through this LED. However, at forward bias, we have some similarity at low forward bias, which is plus 1 volt, 2 volts. It also gives us no current in the circuit. However, there is some so-called turn-on voltage, and for this particular blue LED, it is around 2.5 volts. We start to measure some current flowing through the device and also visually observe blue light emission. And once we have very small step from 2.5 to 3 volts, plus 3 volts forward bias, it results in a huge jump in current from 0.14 to 19.2 milliamperes, which is like more than 1 order of magnitude increase in current, which follows some exponential dependence. So what it means, if we now try to represent it in general, not being very precise with the measured data, but in general, if we represent current voltage characteristic of a blue LED in our case, where we have here voltage, here is current, so we can say that it was very small current, which was barely measurable by our available multimeter. add reverse bias, so here we have a negative bias. Then it goes to forward bias, and current remains very small until we reach some turn-on voltage, which is about 2.5 volts forward bias. So it remains very small and then exponentially increases. So this is general representation of diode current voltage characteristic, very asymmetric, which becomes like this device, which is LED, but it can be also just a diode without this function of emitting light. It was just picked up for more visual demonstration purpose, but both of them are devices, regular diode and light emitting diodes, which possess very sharply defined asymmetric conductivity, which depends on polarity of applied bias to these devices. So this is very simple demonstration how we use power supply, ampere meter and voltmeter to measure current voltage characteristic and get some real data from objects of our investigation in terms of electrical properties. So obviously in labs all this power supply, ampere meter and voltmeter, they are substituted by so-called SMUs, which are source measuring units. So they can do, as one instrument can do this, change, apply bias, measure current and voltage drop over your object of investigation as an electrical device automatically and simultaneously. So here we just combine these different individual tools to demonstrate the basic approach and better understand how we measure current voltage characteristic if there is such a demand and interest to do so. Before we finish this discussion, I just would like to highlight two features of ampere meter and voltmeter. So let us draw this electric circuit we started at the beginning with. So we have some power supply, we have our resistor or diode, whatever we want to measure current voltage characteristic of. We have ampere meter in series, and here is voltmeter. So this is the same electric circuit which we use to measure current voltage characteristic in this experiment. And I would like to highlight, based on how we connect ampere meter and voltmeter in electric circuit, that internal resistance of ampere meter should approach to 0 because it's connected in series to resistor which we investigate and characterize by means of electric current voltage characteristic. So it should not limit current through this electric circuit, should not add any parasitic resistance to resistor under investigation. At the same time, internal resistance of voltmeter should approach to infinity. So we need to be sure that at this junction current which go to voltmeter is approaching to 0. For that purpose, internal resistance of voltmeter should approach infinity. So in that case, we will not alter electric current I, which flows in this circuit and measured by ampere meter A, and by adding voltmeter to this electric circuit and measuring voltage drop over resistor, we will not change current in the electric circuit. That's why internal resistance of ampermeter should be approaching to 0. Internal resistance of voltmeter should be approaching to infinity. So this is some very simple and intuitive statement, but would be good to keep that in mind and understand the key difference between ampermeter and voltmeter. So thank you very much for your attention. See you next time, and follow the channel for new videos. Bye.